Hello, good morning. Today we're going to talk about the topic of control theory. We hope you enjoy. To control an object means to influence its behavior and the way it reaches a desired final point. In order to implement this influence factor, engineers designed and constructed. Mathematical control theory is the area of application-oriented mathematics that deals with the basic principles underlying the analysis and design of control systems. An example of this is the use of difference rather than differential equations when one is interested in digital control. To control an object means to influence its behavior so as to achieve a desired goal. In order to implement this influence, engineers build devices that various mathematics. While on the one hand one wants to understand the fundamental limitations that mathematics imposes on what is achievable, irrespective of the precise technology being used, an example of this is the use of difference rather than differential equations when one is interested in digital control. We all know that control system is the set of devices that work together in order to achieve a desired aim. System, a group of things, principles or procedures such as people, materials, equipment, software, installations, etc. Therefore control is manipulation of a set of the magnitudes or actions to obtain a wished response. For instance, various feedback control systems are used during actual spaceflight in order to compensate for errors from the pre-computed trajectory. Control theory, in other words, refers to the set of devices that work together in order to achieve a desired aim. Feedback, which is another word for response or reaction, or, it can be also used to refer to a method of system control. Mathematically, stability theory, dynamical systems, and especially the theory of functions of a complex variable, have had a strong influence on this approach. To control an object means to influence its behavior so as to achieve a desired goal. In order to implement this influence, engineers build devices that incorporate various mathematical techniques. For instance, physical principles and engineering specifications can be and are used in order to calculate the trajectory of a spacecraft, which minimizes total travel time or fuel consumption. Origins, concepts and ingredients. The word control has a double meaning. First, controlling a system can be understood simply as testing or checking that its behavior. Control theory, the need of automatizing processes to let the human being gain in liberty, freedom, and quality of life. Let us indicate brief degrees how control problems are stated now. The application of the complex numbers in the field of the modern control theory is essential. The dynamic systems are defined through equations that can vary from a or the variable. Complex numbers play a fundamental role in control theory as they are required to evaluate the system, analyze the poles and zeros and perform calculations to model the system. First, we will look at how the system works and its main components and then investigate the relationship between control systems and complex numbers. A closed-loop system is an automatic control system in which an operation, process, or mechanism is regulated by feedback. However, an open loop does not use a feedback system. This tool allows us to convert the input signal and the system's transfer function from time functions to functions of frequency. This simplifies the mathematics used in the system. This method simplifies the process by converting the differential equations into a system of lower-order time-domain equations called state equations. Now we will look at the different ways a system can be displayed. A sensor is the system for measurement of a signal. A plant is the part of the system to be controlled. The controller provides satisfactory features to system. The transfer function f of a system is defined as the ratio between the output and the input in the Laplace domain. where Ys is the output signal and Us the input signal. Here is a diagram with what happens in a simple closed-loop system, where Bs is the feedback signal, E's the actuating error signal, G's the control function, and H's is what allows the output signal to be converted into the feedback signal, also known as the matrix differential equation method, allows us to describe the system by defining a set of n-state variables, output of system, at input of system, xt state of the system, xt first derivative of the state vector of the system. The first is the state equation, the second the output. Poles and zeros of a transfer function are defined as the frequencies for which the value of the denominator and numerator of transfer function becomes 0 respectively. We can examine this function on all points in the complex plane. To find the zeros, we need to look at the numerator. To find the poles, we need to look at the denominator. Poles and zeros also have an order. This is the amount of times which they occurred. Complex numbers play a major role in the topic of stability, but first we need to know what is meant by stability. Suppose we have a system. This system has 0 input. It may occur that the position, state of the system doesn't change in time. Then the system is in an equilibrium position. However, if we place the system in a different position than its equilibrium position, three things can happen. If the system converges back to an equilibrium position, it is stable. If the system oscillates about an equilibrium position, but doesn't converge to it, it is critically stable. If the system diverges, then it is unstable. The root locus analysis is a graphical method for examining how the roots of a system change with variation of a certain system parameter, commonly again within a feedback system. In other words, this is an analytical tool which allows us to determine the different poles and zeros the equation has and whether the system is stable or not. Stable, if its poles are in the right half of the complex plane. Unstable, if its poles are in the left half of the plane. Marginally stable, if its poles are on the imaginary axis. Also, a linear system can be classified into being a minimum and a non-minimum phase system according to its poles and zeros. A system is a minimum phase system if it has zeros in the left half plane. A system is a non-minimum phase system if it has zeros in the right half plane. Maximum phase system, the zeros of the system are in the right half. Mixed phase if in both sides. How does it work? Let's see an example solved. Mathematically, this is just a pendulum to which one can apply a torque as an external force. One of the simplest problems in robotics is that of controlling the position of a single link rotational joint using a motor placed at the pivot. We assume that friction is negligible, that all of the mass is concentrated at the end, and that the rod has unit length. From Newton's law, for rotating objects, we obtain the equation below, in terms of time, using the variable theta. Let us assume that our objective is to apply torques as needed to correct for such deviations. For small theta minus pi. Here we use the standard little o notation. O of x stands for some function g of x. Since only small deviations are of interest, we use the limit as it approximates to 0. We drop the nonlinear part represented by the term O times theta minus pi. Thus, with phi equal theta minus pi as a new variable, which we replace in the equation 1.1. As a first attempt at solving this control problem would be as follows. If we are to the left of the vertical, that is, if phi is equal to theta minus pi and larger than 0. Then we wish to move to the right, and therefore, we apply a negative torque. If instead we are to the right, we apply a positive. That means, we apply a proportional feedback. The obvious solution is to keep alpha less than 1, but to modify the proportional feedback through the addition of a term that acts as a brake, penalizing velocities. In other words, one needs to add damping to the system. We arrive then at a PD, or proportional derivative feedback law. With alpha less than 1 and beta less than 0. In practice, implementing such a controller involves measurement of both the angular position and the velocity. If only the former is easily available, then one must estimate the velocity as part of the control algorithm. This will lead later to the idea of observers, which are techniques for reliably performing such an estimation. We assume here that phi prime can indeed be measured. Consider then the resulting closed-loop system. Then get the roots of its associated characteristic equation that are the ones below, both of which have negative real parts. This convergence may be oscillatory, but if we design the controller in such a way that in addition to the above conditions on alpha and beta it is true, that then all of the solutions are combinations of decaying exponentials and no oscillation results. We conclude from the above discussion that through a suitable choice of the gains alpha and beta it is possible to attain the desired behavior, at least for the linearized model. That this same design will still work for the original nonlinear model, and, hence, assuming that this model was accurate, for a real pendulum. Due to what is perhaps the most important fact in control theory and for that matter in much of mathematics, namely that first-order approximations are sufficient to characterize local behavior. Designs based on linearizations work locally for the original system.